Yeah. So good morning. So we are in the third part of our lecture series on computer architecture. In this lecture series, we have been looking at mainly we are concentrating on the memory hierarchy as well as the I/O subsystems. So we have already covered the memory hierarchy and the cache memory design. So on this lecture, we will be looking at the design of virtual memory, or how the secondary memory and the main memory interacts to provide an illusion that there is a very large memory called as the virtual memory that is available to the user. Then we will look at the I/O system design. When it comes to the virtual memory design, so we saw that in the memory hierarchy you will have the main memory, which is usually a semiconductor based memory. Usually a DRAM based technology is being used in constructing the main memory, where the program will reside. The processor will fetch instruction one after another of the program and execute it. And we can have a level, one level or two level or three levels of cache memories in between the CPU and the main memory in order to reduce the speed gap between the processor and the main memory. But the size of the main memory is restricted because of the cost constraints. But a typical programmer would like to use many applications that are available and would not be interested in being restricted to the size of the main memory. So to this fact, we give an illusion to the programmer that a very large memory is available in which the program can reside and access data and invoke applications, whereas the actual main memory would be much smaller than that virtual memory, which is an illusion that we give. So what really happens is that we realize the virtual memory on slower devices called as the secondary memory and bring the part of the program that is currently needed by the programmer into the main memory and execute it from the main memory. So this design is called as the virtual memory, and we will look into these details in the following slides. So the unit called as the memory management unit takes care of the design of the virtual memory. The CPU or the processor generates what is called as the logical address. So from the point of view of the CPU, a program may consist of, let us say, 10,000 locations or into units, which we will call it as pages later on. So this is the address space that the processor can access, and there may be many processes that may be running, which is being managed by the operating system, and it will allocate 10 different pages, so called, for each of these processes. All these comprises of the virtual memory. So the processor generates addresses which will fall within the address space that is allocated to it. That is called as the logical address, and the main memory management unit translates it into a virtual address depending upon where the pages allocated to this process is being loaded, and this virtual address is where the data is present, and actually a part of it would be brought into the main memory, also called as the physical memory, and will be placed. So first we have to check whether it is present in the main memory or the physical memory. To this end, the MMU or the main memory management unit translates this virtual address into what is called as the main memory address or the physical address. So this address is the one that is being used to search in the main memory. But as we saw, before searching in the main memory, we first look into the cache and check whether it is present in the cache. If there is a cache hit, we will retrieve it from the cache. Otherwise, we will go to the main memory and look into the main memory only if there is a cache miss. Even if there is the data is not present in the main memory because it is not yet loaded, then where we say there is a main memory miss, then we have to go to the secondary memory, okay, and then fetch the data from the secondary memory. So this is the overall memory hierarchy and the way the given access is being completed. So the logical address is the one that is being generated by the process, and it is translated into the virtual address, because the processor may have a family of processors have with various of this belonging to the same family may have different sizes of address bus based on its generation. So the addresses that are generated by the process are called the logical address, and they are translated into the virtual address by the memory management, and then MMU translates it into a main memory address or the physical address. The advantage of the virtual memory is the programmer is not constrained by the finite size of the main memory. The programmer can assume that a very large memory called as the virtual memory is available, and the MMU takes care of mapping from the virtual address into the physical address. For example, here there can be 4 units called as the pages that may be part of the addresses of a process. That is A, B, C, D are 4 pages of with their base address as 0, 4K, 8K and 12K being present in the virtual address, and some of them may be present in the physical address, physical memory. Okay, the corresponding addresses are given here, and each of this page in the virtual memory can be resident in any one of these page frames in the main memory. For example, the page A, okay, with the base address of 0 is present starting from the location 16K. Page B is present in this place and page C is being present. So they can be loaded in any given page frames in the main memory, and we need to have a table which can translate the virtual address to the main memory address, or find the mapping between the virtual page number to the main memory page frame numbers. And some of these pages may not be brought to the main memory, such as D, which is still resident in the secondary memory or disk. So how does this translation between the virtual address to the physical address goes on? As follows. So the virtual address is viewed to have 2 parts, the virtual page number and the page offset within this one. So we divide the virtual memory into finite or fixed size units called as the pages, and there are going to be number of pages in the virtual memory. So every address falls within a page. So this part of the address, virtual address, gives the virtual page number in which the address falls, and this gives the position of the word with respect to the base address of the page or the page offset. So what we first need to do is, the page that is resident in the virtual memory and realized, of course it is residing in the secondary memory, virtual memory is realized as secondary memory. So those pages are as it is in entirety and loaded into the page frames. So the relative offsets of the different words in the virtual page will be the same as the offsets of the words in the physical page frames. So what we need to do is, given a virtual page number, we need to find out the base address of the page frame that is holding it if it is present in the main memory. Once that is there, we can simply concatenate the word offset with the page number, or add the word offset to the base address of the page and get the actual address. So for the mapping from the virtual page number to the physical page number, we use a mechanism called as the page table. This page table has a number of entries, one entry for each virtual page that the process can access, and that entry will tell you the information about, whether the page is valid, whether the page is currently residing in the main memory. If it is residing, what is the base address of the page frame holding that page, and some other access bits that give information that is used for some memory management policies. So here is an illustration telling how the pages from the virtual memory are brought and loaded into the main memory, and what is the correspondence of those virtual pages to the actual pages present in the secondary memory. So here is the virtual memory. So they are divided into units called pages. The size of the pages can be varying. It can be 512 bytes to 8K or 16K and so on. So page 0, 1, 2 up to n-1 pages are being shown here, and Main memory or the physical memory is divided into page frames. The size of the page frame is equal to the size of the page, and any page can be residing in any page frame in the main memory. We don't put restriction. So the placement policy is quite general. Any page can be resident in any page frames. For example, page 0 can be present in this third one, page 2 can be present here, and so on. And actually these pages are residing in the secondary memory, which realizes the virtual memory. So the secondary memory is being achieved by having many secondary storage devices like magnetic storage devices like hard disk, optical storage devices, and so on. So we view the secondary memory in terms of the drive number, the disk number, and the sector numbers, whereas the virtual memory is a monolithic address space where all the addresses are present one after another. So there is a one-to-one mapping between a virtual address and the secondary memory address, but a virtual address may be just a 40-bit number, whereas when it comes to the corresponding secondary memory address, we have to specify it in terms of the device or the drive number, sector number, and so on, track number, and so on. So these pages in the secondary memory again may be present in certain drives in certain sectors within those drives. So the translation from the virtual address to the main memory or the physical address happens in a paged memory management unit as follows. So here the virtual address is generated by the CPU. It has two units, the page number and the offset within the page. Then what we do is the page number is first checked whether it is a valid page. For that we have a register which stores the page table limit register. So for every process the valid number of pages that it can access will be present in this one. So we check whether this page number is less than this valid page numbers that the process is allowed to access. If there is a violation, a bound error is being generated. Otherwise what we will do is we have to check within the page table the information about this virtual page number. So every process will have a page table that stores the information about the every virtual page that process can access, and the base address of the page table of a given process is stored in a register called as the page table base register. So when the CPU schedules a process, it loads in this page table register the base address of the page table of the process that is scheduled. So if there is a context switch from one process to another process, then the incoming process has to access its own page table. Therefore this page table base register will change its value from the base address of the outgoing process to the base address of the page table of the incoming process. So with using this page, the entry of the page table base address as the base, at the beginning address of the page table, you use the page number as the index and refer the entry in the page table. That is called as the page table entry. So this entry will have information about this virtual page. So the if there are different bits may be present, they are called as the access control bits. One bit is the one of the bits in that access control field is the presence bit that tells whether the page is currently resident in the main memory or not. If the bit is reset, it means it is not present in the main memory. Then we say it is a page fault or a page miss has occurred. If it is resident as indicated by a 1 in the presence bit, then this field gives you the base address of the page frame holding that virtual page in the main memory. So you use this base address or the page number, page frame number, physical page frame number, and concatenate with the offset to get the physical address. Then it can be retrieved. Other bits which are needed for the memory management or the usage bit, which will give an indication of how many times this page can be used. If it is a more useful page, it has to be retained. So a replacement policy can use it. A bit called as the dirty bit will tell whether the page has been modified after being brought in. If it is brought, as soon as it is being brought in, the dirty bit will be reset, indicating that it has not yet been modified. And whenever there is a one or more write operation that goes on in the page, the dirty bit will be set. It tells that the page has been modified. When a page is being replaced and if the dirty bit is set, then the page has to be updated in the secondary memory. So these access control bits are used to this end. So a typical page table entry corresponding to a virtual page in the page table will have this kind of a format. One, a valid bit will tell whether this page is valid or not. To begin with, a page may be allocated certain number of pages, and if the page requests for more pages, then the OS can allocate more pages and sets the valid bit of those pages to be 1. So validity is being checked by looking at this bit. Then the reference bit and the modify bits are all present here. Protection bits is being used to control the read-write operation that can be carried out. So certain pages can be only read, certain pages can be read or written, and so on. So those access control bits control the op that is being performed on those pages. And if it is present, the page is resident in the main memory, then the page frame number is given in this field. So what we have looked at for is the concept called paged memory management, wherein the virtual address space is divided into fixed size units called pages. The advantage of this division of the virtual address space into fixed size is that we can have a page table where we know, given a page frame number, we can easily calculate the base address of that page, because the page number into the size of the page will give you the base address. So that is the advantage of dividing the virtual address into fixed size units called pages. But it has a certain inherent disadvantage, because you will allocate certain number of pages, integral multiples of pages for storing the program. But the size of the program may not be equal to the integral multiple of pages. On the average, the last page will only be half filled. Because of that, there is a wastage. This wastage occurs because the arbitrary sized program or units or routines are being loaded into fixed sized units called pages, and this wastage is called as the internal fragmentation because it occurs within a page. So there is and setting this access permissions like read write tags for these pages, okay, is also another matter of concern. The other way of looking at managing the virtual memory is called as the segmentation, where we view the programs as a number of routines. For example, you may have a main program or a main routine which is accessing many subroutines. So there is a subroutine 1, there is a library routine, maybe called as the square root. It may use a stack as a unit, or it may use some symbol tables and so on. So each of these are some logical entities which are being accessed by the main program. So in a typical modular programming language like C, if it is being used, we generate a number of procedures or modules, and each modules will be a finite size, usually kept smaller in order to control the complexity of programming and maintaining the software. So we view the program in terms of many modules, and they can be of varying sizes. They may not be a fixed size. So we call each of them as segments. So we may call this as segment 0, segment 1, segment 2, and so on. So we can view the virtual memory to consist of a number of varying sized units called segments, and these segments can be brought and loaded into the main memory, which again will be of varying size. If you do so, then we have the concept of segmentation, in which case you should maintain what is called the segment table, which keeps track which segment in the virtual memory is currently residing in which location in the main memory, and so on. Because the segment size can be varying, in addition to holding the base address of a given segment, you should also store the size of the segment. So the segment table should have two entries, one the base address, another the limit or the size of the segment. For example, you can see that for segment 0, which is in this one, the segment 0, it's being loaded in the physical memory here. So its base address is 1400 as given here, and the size of the segment 0 is 1000 bytes. When it comes to segment 2, its base address is 4300 as given here, and the size is 400. So we need the base address as well as the limit or the size of the base when you maintain the information about a segment in a segment table. So you may have a number of segments in the virtual memory and bring them and load into the main memory as and when they are needed. When they are no more required, you can retrieve the space and use it for loading some other segments. So the segments may not be present in the main memory in a contiguous manner. So soon when we start swapping many segments in and out of the main memory, so you may have different segments that are present in different locations. For example, segment 3 may be present at the starting from the lowest address. Then you may have a segment 9, and they may not even be contiguous. You may have gaps because there might have been a large segment starting from this location to this location, and we have removed it, and therefore later a segment 6 has been brought in, and so on. So gaps may occur between segments, and this leads to a wastage, and it is called as the external fragmentation because it occurs external to the segment. So this is the wastage associated with the segmented memory management. Coming to the mapping, so the virtual address is now viewed to have two parts, the segment number and the offset of the word within the segment. Then the segment table entry will have the following information. One, certain access control bits such as the presence bit and modified bit. Presence bit tells whether it is present or currently loaded in the main memory, and modifier bit may tell whether after bringing to the main memory whether it has been modified at least once, which is used during updating or replacing the segment. Then the length of the segment and the base address of the segment. So how does the translation work? So given the virtual memory address generated by the CPU, you first check whether it is a valid segment by comparing the segment number with the limit register. Okay, if it's an invalid segment, similar to the paging, a bound error occurs. Otherwise, you use the base address of the segment and use the offset to access the corresponding word in the given segment. So in terms of segment table, the address translation, we call this as the dynamic address translation from the virtual address to the main memory address. For the segmentation works as follows. So the program generates a virtual address which has the two parts, the segment number and the offset D. So what we do is the memory management unit responsible for the segmentation, okay, has a segment table, one segment table for each process, and the base address of that segment table is loaded in the register called as the segment table base register or the segment table pointer. So you are referring to this particular segment, maybe segment number 10. So that is present in a segment table entry at the index 10 with respect to the base address. So what we do is you use this base address and use the segment number as an offset from the base address and go to this what is called as the STE or the segment table entry. So and refer information about the segment. If it is present, then you use the length field and the base field to generate the physical address. So what you will do is you will use the base field that is present here and the offset, concatenate it, or add the base address plus the offset to generate the physical address. So during this part you should also check whether the length, the offset is less than the length. D should be less than the length, because otherwise you are trying to refer to an word outside the segment. So once it is generated, so this is where in the main memory the segment is being present. This is the base address and this is the offset with regard to the base address. You go and retrieve the word from the corresponding location. So what we saw is you may either use segmentation or paging. Paging have fixed size units. Segmentation has the convenience that it allocates variable sized units which corresponds to modules or routines of a program. The advantage of using segmentation is that it is easy to view the virtual memory in terms of many modules corresponding to different programs, and it is also meaningful to access allocate read-write access permissions, because you allocate read-write access permissions in terms of the modules. For example, the subroutines, okay, are usually given only a read access permission. You don't overwrite a subroutine because you are using it as a library routine for achieving a functionality like printing into the file or interacting with the IO devices and so on. So that is the advantages of segments. But the problem with the segmentation is that a given segment can be a very large size. When you have to bring and load a segment into the main memory, you may end up bringing a very large segment into the main memory which occupies large amount of space in the main memory, while the actual content that you want may be a small part in the segment. Or in other words, the working set of the program may be only a small part in the overall segment that is being brought. Then a phenomenon called as the superfluity comes in, that is, you bring more information that is currently required and it simply occupies more space in the main memory, possibly replacing some other useful segments. So to avoid this, we can use the advantages of segmentation and paged memory management together, and thereby we get what is called as segmentation with paging, wherein we divide the entire virtual address space into units called segments. But now we put a restriction that segments cannot be of arbitrary sized units. It has to be integral multiples of units called as pages, which is of fixed size. So we have got every given virtual address space as falls within a particular segment. Each segment has got a number of pages and therefore it will fall within a particular page, and then the given word will be at a particular offset within the page. So how does the translation will happen? So you will have a segment descriptor which is similar to the segment table of segmented memory management. Given the segment number corresponding to the address which we need to translate, you refer to the corresponding descriptor, the descriptor corresponding to the segment number. So this descriptor should have information about the segment, but this segment is being divided in terms of pages. So it will in turn point to a segment table holding information about all the pages present in the segment. So this pointer will be to a particular page table. Then you use this page number to refer to the particular page table entry in the page table that will have information about this page in this segment. Then if it is present, then you use the base address of the page frame holding the page and use this offset to retrieve the word. So there are two levels of translation. One, you go through the segment table, next you go to the page table. Here is a more detailed illustration. So here you have got a number of segments. Each segment has got a segment descriptor, that is the segment 0 descriptor is present here and so on. Each descriptor will have a pointer to the corresponding page table. For example, this is the page table corresponding to segment 1. For segment 3, this is the page table. Then use the page table page number to go to the corresponding entry within the segment and use it to check whether the page is present and use the offset to generate the physical address. So it again may have different access fields like this. So this is a much more detailed illustration of how this translation works. Given the segment number, page number and the offset, the first stage you refer to the segment table using the segment number and using the base address as given by the segment table base register. Okay, you go to the corresponding index in the segment table. This gives the segment descriptor of this segment number, and this will be nothing but a base address of a page table. Use this page number as an index to this base address and goes to this page table entry, and then use this if it is present, use the page number, okay, or the frame number, and add it with the offset to generate the physical address. So this is the next evolution in terms of managing the virtual memory. There are other variations also that are present. It so happens that suppose the virtual address space is very large, the number of pages present in the virtual address space itself may be so large that each page table itself may be very large, and these page tables are difficult to access. And actually these page tables have to be stored somewhere. We usually allocate a part of the main memory to store these page tables or segment tables. In this case, what we can do is we can have not just one level but multi-level page tables. So we will have pages which are themselves being paged. So you will have two levels of translation for paging. That is one way in which we can manage the large virtual address space. Another way is what is called as the inverted page table. So the page table is supposed to hold a number of page table entries, one for each virtual page. If the number of virtual pages is large, the page table is larger. So the other way of tackling this issue is to have a table which has got one entry for each page frame of the main memory, and therefore the size would be restricted equal to the number of pages present, page frames present in the main memory. So wherein we should store the virtual page number and the page frame address of those pages that are currently residing in the main memory. But the problem here is that searching this table would be difficult, because any given virtual page may be residing. If you are searching for a given virtual page, you should check for all entries within this table. This table is called as the inverted page table, and searching becomes difficult. You can use an associative memory for doing the searching, but it is not a practical one when it comes to using an associative memory for implementing inverted page table. The other method is to use the technique called hashing. Given the virtual page number, you use a hash function to generate an index or a key, okay, and this key is an index into the inverted page table where the information about this virtual page would be present. So hashing function takes page number from a very large but sparsely populated address space and then maps onto a smaller address space. So using this, you check the entry. This entry can be used to check whether this virtual page is present or not. So if it is present, then the corresponding PID or the page number is being used along with the byte offset to generate the physical address. Now we saw that we can go in for either paged memory management or segmented memory management or multi-level page memory management or inverted paging or memory with paged segments or any one of these schemes to do the translation from the virtual address to physical address. But again this has a large overhead, because you would see that given a virtual address, you need to first convert it into the physical address by referring it into a table, page table or segment table or any one of them. Then you have to again fetch the data from the main memory, which means there are two main memory references that are needed. One to refer to the table and another to actually fetch the data. So this consumes more time. We want to reduce it. Another aspect is that supposing you generate an address which falls in a page which is of size, let us say 4K, then it is very likely that successive accesses will also fall within the same page. So every time an address within a page is being generated, if you go in for a dynamic address translation, that is converting the virtual address to the physical virtual page number to the physical page number, is an unnecessary. Instead, what we can do is, once a virtual address page number is converted to a physical page number, this mapping can be stored in a high speed memory, so that this mapping can be used until it changes or until this virtual page is being removed from the main memory. So such an high speed memory holding some of the recently found out mappings of the virtual page number to physical page number is what is called as the translation look-aside buffer. So it contains the page table entries that has been found recently. So it has got the virtual address and the physical page frame number mappings. So given a virtual address, the processor examines this TLB. If a page table entry is present in the TLB, we say that there is a TLB hit. Then the frame number, page frame number, is simply retrieved from the TLB and it is concatenated with the word offset to generate the real address, that is the main memory address. If an entry is not present in the TLB, we say that there is a TLB miss. Then only we go in for the address translation using the page table or segment table. Once such a mapping is being found, then what we do is we update the TLB entry so that it can be of use in the future accesses. So the implementation of the TLB will look as follows. So you have got a TLB, translation look-aside buffer, and in order to search the TLB quickly, usually this TLB will be an associative memory, which means that it has got a pair of key and content. So given a key, it will parallelly compare the search key with the keys that are being stored in different locations and will give out whether there is a hit or a miss in a time that takes only one comparison time. So given the virtual address in terms of the page number and the word offset, then what we do is we associatively look for this page number in the TLB. If there is a TLB hit, then we go to the corresponding TLB entry. So you will have this virtual page number and the physical page number pairs along with some other access control bits like this one. So you directly take the corresponding page number or the page identification. So concatenate this physical page number with the word offset to generate the physical address. You can have again some control bits like presence bit, okay, or dirty bit, okay, whether this entry is valid and so on, usage bit for the replacement and so on. Again the TLB can be updated whenever a mapping is found. You can load the TLB, in which case you have to invoke a replacement policy. LRU replacement policy can be used to update the TLB and so on. So now we have looked at the virtual memory management using paging segmentation and then TLB, which does the dynamic address translation easier. We have also looked at the cached memory management. Now putting it all together, how does the entire memory hierarchy work? That is what is being illustrated in this whole diagram. So the CPU generates a virtual address. First you have to translate it into the physical or the main memory address. For the same, you first look into the TLB. So search in the translation look aside buffer. There can be a hit or a miss. If there is a TLB hit, then you can directly retrieve the physical address, physical page number corresponding to the virtual page number. Use it along with the offset to generate the physical address. Once you have got the physical address, then first search in the cache. So you search in the cache, again there can be a hit or a miss in the cache. If there is a hit in the cache, then you retrieve the word and return the data from the cache to the processor. If there is a miss in the cache, then you retrieve it from the main memory. You have already checked that it is present in the main memory because the TLB has given corresponding page frame in the main memory which holds it. So there is definitely a main memory hit. So you retrieve it from the main memory, load it or update it into the cache, and then retrieve the word and give it to the processor. On the other hand, if there is a TLB miss, then you have to go in for what is called as the dynamic address translation here. So now this whole dynamic address translation, okay, goes through by referring into the page table or segment table. So in this case it is the paging that we are considering. So you search the page table and check whether there is a hit or miss in the page table. If there is a hit in the page table, which means the page is currently resident in the main memory, then you generate the physical address, because use the page frame base address along with the or the page number. You then update the TLB, because you know the virtual page number and the physical page number. You store this pair in the TLB for future usage. Then this is being physical page number is being used here to again go and then search in the cache and so on. In case if it is if there is a miss in the main memory, then you go and then fetch it from the secondary memory and then update the main memory page table, because I create an entry in the replace one of the pages and create an entry, page table entry, and update it in the, store it in the main memory, and also update the TLB and so on. Well, so now we will talk about how the memory management policies for a virtual memory works. The policies that we use for paged memory management as well as the segmented memory management are more or less same. Well, in the case of placement, pages can only be placed in fixed size units called page frames. So any page can be loaded into any page frame. So that is how the placement policy will work. It is similar to the fully associative cache memory technique. Then when it comes to the segmented memory management, placement depends upon, you have to find a particular contiguous memory location in the main memory which can hold the segment. So you have to first check where it is present. There are different policies like best fit, first fit method of identifying a hole. What we call as a hole is the contiguous memory location, address locations currently which is available. So we identify a hole and place this segment and manage it. That is all about the placement policies. Then there are replacement policies. Suppose a page has to be brought and all page frames are being occupied, we then choose one of the existing page and use it for replacement. So that is called as the victim page. So there are various page replacement techniques that can be used. So if there is an unused frame, you use it. If no unused frame is available, select a victim frame using a replacement policy. Then you check the dirty bit of it. If it is not set, it means the page has not been modified, you can simply use it. Otherwise, if it is dirty, you write into the disk. Then invalidate the page table entry and the TLB entry, because you are going to replace it. The corresponding page table entry which tells that the page is residing in the main memory is wrong, because you have removed it from the main memory. So you have to change it. And the TLB entry will also be wrong, because the VAPA pair, virtual address physical address mapping, will be wrong because the page page has been removed. So they have to be invalidated. Then they load the new page in that page frame by bringing it for accessing from the disk, and then you update the page table entry as well as create an entry in the TLB, and then you restart the program which has resulted in this page miss. Well, how we decide on the page replacement algorithm? So naturally we want a very low page fault rate. So we have to use a method which reduces the number of page misses that occur, because whenever there is a page miss, the process that is running is being suspended until the page is being brought. So there is a difference between how the cache miss and a page miss is being handled. Page misses result in context switch and process is being suspended. Only after the page is being loaded, again it is being put into the ready to run queue, and then it is being scheduled. So page misses are costly, so we have to reduce it. We can see how a page miss is handled by looking at the reference string, which is the string of pages that are being referred by a program. A typical reference string will look like this one. First we have got an optimal algorithm proposed by the B-Lady, and what it does, it looks at the future page references and try to retain those pages which would be required in the future. Naturally this is not practical because you will not be able to know what are the future references that are required. It is just used as an hard yardstick or a benchmark in order to check other replacement policies. Okay, so here is an example, that is, so this is the reference string of pages that are being referred. So page 7 is being referred, so it is being brought and loaded, then 0 is being loaded, 1 is being loaded, then let us say 2 is being referred, and therefore there is a page miss. Then what we do? We identify that page among these 3 pages 0, 1 and 7 which is not needed in near future. So you can see that 0 would be required here, and then 1 would be required here. 7 is not required immediately, so you remove 7 and then load 2. Then let us say a 0 is fetched, it is a hit, 3 is referred, it is a miss. So again you have to go in for a replacement. Among 2, 0, 1, you would see that 1 is the one which is not immediately required, so it is only required here. So you remove this 1 and load the 3 into this one. So again 4 is required, then you look into this one, 2 and 3 are immediately required as compared to 0, so 0 is replaced by 4 and so on. So this is the optimal B-Lady's optimal policy which reduces the page misses and so on. There are also other methods which is a not recently used method which tries to approximate these replacement policies. It has 2 bits, one is called the reference bit and the modifier bit. So whenever a page is being referred, the reference bit is being set as 1. When a page is loaded, both the reference and modifier bit are set as 0 because it is not referred, it is being not modified. Whenever it is referred, that is, it is then reference bit is set as 1. If it is modified, then again the M bit is also set as 1. Then at the time of replacement you check for pages which has bits both R and M as 0, 0, which means that it is not being referred, not being modified, so it can be removed. Otherwise you check whether it is how it works, okay, one of these, and then access it. Then we have got the FIFO method, first in first out, or the largest resident time replacement. You evict the page which has been brought into the main memory in the distant past. Okay, a phenomenon called as the B-Lady's anomaly occurs when you use the FIFO, and therefore FIFO is rarely used in practice. You will see an example for this B-Lady's anomaly. Let us say this is the reference string that is being generated by the process. So we have got two cases. One uses one has a main memory having 3 pages, another has a main memory having 4 pages. Naturally, which means that this case is the one where the main memory pages are larger, therefore it should reduce the misses. But we will see that indeed it has got more page misses as compared to a main memory where the number of pages is less. For this reference string we can see that page 1 is being referred, so 1 is put, then 2, then 3, then when the 4 is being referred, because 1 is the oldest frame, it is being replaced, then when 1 is required, then 2 is being replaced by 1, then when 2 is required, 3 is being replaced by 2, then 5, 3, 6 replaces these, and so on. So over a sequence of 1 to 5, we will see that 9 page faults have occurred. Whereas if you have, for this case of 4 page frames, when these first 4 references will bring in 1, 2, 3, 4 into the main memory, 4 page frames, and this would be the content of the main memory. Then the access 5, okay, then 1 and 2 would be an hit, then the access 5 will replace 1, okay, because it is the oldest one, then the access 1 will replace 2, 2 will replace 3, 3 will replace 4, and it goes like this one. And for this case you would see that there are 10 page faults that has occurred, which is more than this. So this is what we call as the B-Lady's anomaly. What it tells is, for a given number of page, here we have changed the number of pages here, okay, and we have found out the page faults, number of page faults for a given reference string. You would see that when the number of pages changes from 3 to 4, the number of page faults actually increases before decreasing, okay. So this phenomenon is what we call as the B-Lady's anomaly. FIFO has got this problem. We have then a technique called as the least recently used LRU policy, which you have already seen related to the cache memory management. So what it does, it among the pages that are present in the main memory, the one that is being least recently used is the one that is being replaced. That is, most recently used pages are being retained, least recently used is being removed. So if you have a reference string 1, 2, 3, 4 like this one, then you load it into the main memory like as follows. Then when the 1 is required, then 1 is required, it is a hit, then 2 is also a hit. When the 5 is being referred, then you will find that among those that are present, 3rd is the one which is least recently used, therefore 5 replaces 3. Then 1, 2 is again a hit, 3 is again a hit, and then when 4 is required, among these 5 is the one which is a victim, and therefore you replace 5 and then load 4 and so on. So this is how the LRU policy works. It can be implemented by maintaining an LRU stack, okay. This is another way in which the LRU page replacement is being shown. So 7 is being referred, it is loaded, then 0 is loaded, then 1 is loaded. When 2 is being referred, it is a miss. Then among this one, 7 is least recently used, so you replace 7 by 2. Then 0 is a hit, 3 is a miss. So among the one that is present, okay, 0 and 2 are referred, 1 is not required, so you replace 1 by 3 and so on. So there are 12 page faults from 6 LRU gives, whereas if you have used the FIFO, you should have given 15 page faults. This is the LRU stack which can be used to maintain an LRU replacement policy to work. So what we will simply show in this slide is that how the LRU stack is being updated. So here, as you would see that the most recently used page is maintained here. We will call it as MRU, most recently used. The LRU or the least recently used will be at the bottom of this stack. So whenever there is a page miss, then the page is being brought and it should become the most recently used, and all other, and it will replace the least recently used one, on all other page numbers, their count will increase by 1. So they will be pushed by 1. So you will push the stack with the MRU block. On the other hand, if you refer to a already existing page, then that has to be moved to the top. For example, here you have got 21074 is what is the content of the stack at the time at the point A. Now 7 is being referred, which is already present here. Then you bring 7 and load it here and push all these by 1 unit. So 7 is loaded here, 2 has come here, then 1 has come down 1 unit below, and then 0 and so on. So this is how the LRU stack is being maintained. Okay. There are approximation algorithms that can be used which mimic the LRU but do not have the complexity of the LRU policies. So so you can have just 2 bits which can be set based on this. An approximate LRU method can also be used. The question next is, when will you replace a page or evict a page? Okay. What happens is that an operating system process called as the paging daemon is being frequently invoked. It makes periodically as a result of a clock interrupt. Then it looks at the entries of the page table, look at the usage bits and so on, applies a replacement policy, and based on that it marks those pages which can be evicted. So it sets the valid bit as 0. Then it does not immediately replace all of them, because only at the time of a requirement of replacement you have to remove it, but it simply marks that and tells if it is a dirty page, then it schedules it for replacement, otherwise it simply makes it set the valid bit as 0. Now if there is a page fault, okay, if the desired page is marked but it is still in the memory, you start using it because it is still not being removed, you can start using it. Otherwise, if it were dirty, you load it into the secondary memory and then bring a new page. So this is the advantage, because at the time of you don't need to invoke the replacement policy at the time of replacement, because it was done at periodical basis, and the pages which can be potentially replaced are being marked by the paging daemon. Okay. So we have looked into the concept of the virtual memory management. If you have any questions, you can post it into the chat session. I will address it. So there are basically 3 questions. How many parallel searches can be done in page entries? No, parallel search cannot be done because there is no need, because you know the virtual page number. The page table has got 1 entry each virtual page. You directly go to the page table entry and the corresponding information about the page can be found. There is no need for searching. That is the advantage of having page table having 1 entry for each possible virtual page. Okay, when there is a dirty bit, if it is written into the main memory, why it should be written to the disk, why not to the main memory? It actually, the content of the page is present in the main memory already and it has been modified. That is why the dirty bit has been set. If you are going to remove the particular page from the main memory in order to bring a new page, then naturally you have to restore the content in the secondary memory. That is why you are writing it. The purpose of the dirty bit is if a page has been brought or a segment has been brought and if it is never being modified, there is no need to update it in the secondary memory at the time of replacement. You can save those operations if you know whether it has been modified at least once. That is the use of the dirty bit. In an LRU policy, if a page is being replaced and then if I need it, what do I do? Again it has to be brought in by replacing some other page. So this is how it is being handled. So now we will get into the next part of this lecture, namely the I/O subsystem. So in the I/O subsystem, basically we are interested in interfacing a number of I/O devices with the processor. So I/O subsystem will have a number of I/O devices connected to the bus, which already interconnects the processor and memory. So this is the structure of the I/O subsystem. Our idea is to manage the interaction between the I/O devices and the memory with the help of the processor. So the main problem is we have I/O devices which wants to read or write the data from the main memory. So how do you make it happen? For that you use an DMA controllers, direct memory access controllers, which can access the main memory and make an interaction between the main memory and the I/O devices directly without the intervention of the CPU. More details is that given a number of I/O devices, first we have to look into how the I/O bus structure is being organized. An I/O bus will have basically three parts: a group of lines which comprises the address, another group of lines which comprises the data. So this address lines can be used to uniquely identify an I/O device. Data lines is for the transfer of the data between the memory and the I/O devices, and the control lines to tell the direction of transfer and for the handshaking purpose. So to this bus we do not directly connect the I/O devices, we use an I/O interface in order to connect it. The I/O interface jobs are the following: it uses the address of the I/O device, decodes it and identifies whether it is this address corresponds to the corresponding I/O device or not. Then it has control circuitry to generate the appropriate handshaking signals. Then there are certain registers called as the status register, control register, which is used for the purpose of data transfer. So a bus is nothing but a shared communication link or a set of wires, okay, which can be connected to a number of devices. So a processor, memory and many I/O devices may sit in it. So the advantage is that it is versatile, new computers can be easily connected to it. It is a low cost because it is being shared, okay, but it is becomes a bottleneck because through a given bus only one transfer can be possible. So that would be the bottleneck, okay. Again, the number of devices, that can be a restriction, and the length of the bus will also be a restriction because, okay, the length of the bus is larger, then problems like clock skew will come into picture. So there can be given a bus structure, there can be a bus master which may be controlling the transfers and the bus slave. Usually the processor, the CPU will be the bus master and the I/O controllers are the bus slaves. There can be two sets of lines that can go. One is the control lines which is being initiated by the master and tells how the interaction should go on. Then a set of lines called as data lines, but they can carry the data, the address and also read write control signals. So the master issues the command or the request, then the slave receives and then performs the desired action. So it can be an input or it can be an output operation. So the types of buses are as follows. The processor memory bus is an high speed bus, but only for a small or short intervals, okay, and it is run at the speed of the processor. So it matches the speed of the memory systems and it will offer the bandwidth of the memory as well as the processor. So it is usually optimized for transfer of blocks from the cache memory to the processor or from the main memory to the cache and so on. Then the I/O buses can be an industry standard buses like SCSI or USB, okay. It can accommodate a wide variety or range of devices, I/O devices, okay, or there is a backplane bus, okay, which is again industry standard, in which many IO devices can be plugged in, like ATA or PCI interface devices and so on. The buses can be of two types, synchronous or asynchronous. A synchronous bus, for example, the processor memory bus is a synchronous bus. It is controlled by a clock, okay. Its clock is a part of the signals that go between the two devices, and the protocol is also very simple because it is assumed that both devices are synchronized by this clock. So the relative timing when the transfer will occur is being implicit. So it is advantageous because very little logic is involved and it can run very fast. But every device that has to communicate should run at the same speed of the master clock, okay. And to avoid the clock skew problem, they have to be close by. That is the disadvantage of the synchronous bus. Asynchronous bus are used mostly for IO devices. They are not controlled by a common clock, so we need handshaking protocols. For example, one device may tell that it is ready to read, another device has to give an acknowledgement, then the data has to be put and it has to be marked by a data ready signals and so on. So these handshaking signals makes the devices slower. But it can accommodate a wide variety of devices of varying speed, okay. And it can also be of the distance between the master and the slaves can be very large because there is no clock skew problem in this case. For example, this is an asynchronous bus handshaking protocol because between a memory and the IO device, okay. We need to a data transfer from the memory to an IO device. So to this end, the read request is being placed by the IO device. So IO device signals the request by telling read request, by putting a 1 on the read request, and also puts the address from where it wants to read. In response to that, the memory sees the read request line going from 0 to 1 and also reads the address. So once it has read the addresses, it acknowledges by making the acknowledgement to go high, okay. Once that happens, the IO device sees this acknowledgement indicating that the master has read the IO address. So it releases the read request, it makes it back to 0, okay. And the data line is also being removed because the address is being removed. So the memory then uses the same bidirectional lines to place the data. So the memory sees that the read request line has gone to 0 and therefore it drops the acknowledge, okay. Then the memory reads the then it places the data on the bus and it tells that the data is ready by making this data ready signal on, okay. Then this is used by the IO device. IO device sees that the data is ready, takes this data, okay. First it makes the acknowledge that it has seen the data ready signals. Then the memory takes the data and then the memory finally acknowledges, okay, and this then drops the data ready signal. So in this manner a number of signals have to be exchanged and a protocol has to be followed for every interaction, but the speed of the IO devices, the memory can be different. There is no assumption on how fast an IO device is, but it has a lot of overhead in terms of handling the handshaking signal and applying the protocol, okay. So next, when we have a number of IO devices being connected, there is a need for bus arbitration. That is, potentially many devices would like to take control of the bus, then we can only allocate it to one device. So which device is going to take the bus? So how the bus is being given, okay. So that is what is called as the bus arbitration policy. There are two principles that you follow. One is priority, another is fairness. That is, different devices will have different priority. So the highest priority device should be given priority in granting the bus, okay, and it should be serviced first. At the same time, there has to be a fairness in the sense that even the lowest priority device is not deprived totally from the IO interaction. Of course, these two are conflicting issues, conflicting requirements. We have to strike at a balance while giving the bus arbitration. The following are the different bus arbitration scheme. One is the so-called daisy chain arbitration scheme. Next, you have got the centralized parallel arbitration scheme. Then you have got a distributed arbitration by self-selection, in which each device, okay, a set of lines would be there. If there are capital N devices, there will be a log n to base 2 lines which can hold an address of the device. Those devices which are interested in making a transfer will put its address on that one. So then if a 0 as well as a 1 is being put on a particular line, then it can be read as 1 by the arbiter. So finally the arbiter will read the highest address that is being placed on this lines, and the bus is being given to this one. So this is a way in which arbitration can be given. Then there can be a distributed arbitration using collision deduction, as it is being done in Ethernet or the CSMA or CD protocol is being used. First we will see some of the simplest arbitration scheme followed by the IO devices, the daisy chain. So you have got n devices, device 1 has got the highest priority, device n has got the lowest priority. So they are arranged in one particular order. Then each of this device can make a request, and it can also, after using the bus, it can give a signal called released, and it has also called as an acknowledge signal that goes inside it. So now what we do is, the request lines of all these are being wired or and given as a common request to the bus arbiter. So in response to that one, then the bus arbiter sends an acknowledgement. But this acknowledges first goes to the highest priority device, and if it is the highest priority device has not made a request, it simply passes this acknowledgement to the next device in the line. Okay, so it goes to the next device. Supposing device 1 has requested, then it takes this acknowledgement and starts using the bus. Further, it stops the acknowledgement from going further down this lane. Therefore, when acknowledgement is being generated, it is stopped or consumed by the first encountered highest priority device. So that is why it is called as the daisy chaining. When the device has finished with the bus, it releases the bus using this line, which is again a wired OR signal. So then the bus arbiter is ready for another arbitration cycle. There is a common data address bus which is being shared by all these devices, but at any given time only one will take control of the bus and make use of this bus. Okay. The advantages is it very simple, but the disadvantage is that, okay, highest priority is, of course, priority is being restored, but the lowest priority device may be totally deprived. Okay, that is it is not fair. Then there is a centralized parallel arbitration scheme, wherein there are n devices being connected to a particular bus arbiter. Each device has got a signal called as the request signal, which goes to the arbiter, and it gets an acknowledgement back from the arbiter. So there are n request signals which comes to the arbiter and n acknowledgement signals which goes to the respective devices, okay, and so on. So when one or more devices makes a request which comes into the input of the bus arbiter, it applies a arbitration policy and decides which device should get an acknowledgement and sends the acknowledgement over that particular device. So advantage is that it is flexible. You can even change the priority level of different devices. It can be made fair. Disadvantage here is that more number of signals which go in and come out of the orbital, so it is more complex. Okay, so that is the disadvantage. Then communication between the IO devices and the processor. Okay, how does it happen? So you have a case where the processor directs the IO devices. It makes the transfer to happen using specialized IO instructions. For example, in the 8085 processor, you have got instructions like in and out, which are specialized instruction wherein devices are treated as IO devices and transferred. Alternatively, you can treat the IO devices as if they are memory location, and such mappings are called as the memory mapped IO. A part of the high order memory address is being reserved, wherein these addresses are nothing but the addresses corresponding to IO devices or the IO device registers, IO controller registers. So read or write to these memory addresses are interpreted as commands to these IO devices. To the status register you can read, to the configuration register or control register you can write, and so on. Generally these locations are accessible only by the OS, so only through the OS these IO interaction can be initiated. So how does the interaction between the IO devices and processor can happen? Polling, that is, the processor can periodically check the status of the IO devices to decide which IO devices are interested in doing a transfer. So the processor is totally in command in the sense that through polling it decides which device has got a request and it grants it, and it makes the interaction possible. It also means that it is not only in just control, it does most of the work by itself. Therefore, the processor is being occupied with this one. It wastes a lot of the processor time due to this overhead. Alternatively, we can go in for what is called as the interrupt driven IO, wherein an IO device, whenever it wants the attention of the processor, generates an interrupt, and the processor handles this by running an interrupt service routine or ISR. Well, coming to the IO bus structure, there can be three kinds of IO bus structure which can be thought of. One is the isolated IO, wherein you will see that the memory devices and the IO devices are being controlled by separate sets of buses. Control, address and data buses for memory are distinct from the control, data and address buses of IO. So that is called as the isolated IO. Another where the address and the data bus are being shared by the memory as well as by the IO system, whereas the control signals are different. You have got separate memory read, memory write signals, separate IO read, IO write signals, and so on. So the control signals are separate. They are called as the shared IO. Then you have got the memory mapped IO, where there is no distinction between the memory and the IO devices. Both of them share the same set of address, data as well as the control signals. The interaction between the IO devices and the processor can happen through what is called as the programmed IO. So the device is being polled and looked for the readiness for the operation, or it can be driven by an interrupt. Then once it is ready, by looking at the status bit, then the processor interacts with that one by issuing the IO commands. So here is a programmed IO device interface will look like. So the CPU has got the address bus, data bus and the control bus, which is connected to different devices like printer, keyboard, disk drives through their respective IO interfaces or IO controller. For example, there can be a disk driver or a keyboard driver interface and so on. Each one would be a typical IC which takes care of the interaction between the device and the CPU. For example, they may do a serial to parallel conversion or parallel to serial conversion and generate the handshaking signals and take control register on how the transfer should occur, and at the end it may store or give the status to the CPU to indicate how the interaction or transfer went on and so on. Those are the purpose of these IO interfaces. A typical interface will have the following thing. It has an address decoder to decode the address that is being placed to identify the IO devices, whether it is this IO devices that is being referred by the CPU. Then it has got in and out port for the interaction. So if it is an input device, it takes the value through this input bus, or if it is an output device, it passes the value written by the CPU through this one. Then there are command register and status register. The CPU may write a command word into this command register telling that how many bytes have to be transferred, okay, and so on. Then at the end of it, it may store a status to be read by the CPU to understand how the interaction or transfer went on. Then the transfer can be of three types: synchronous, semi-synchronous or asynchronous. In the synchronous one, it is controlled by the processor or master, and it happens in synchronization with the master's clock. So the master inherently assumes that the device will be ready to transfer the data in a given clock cycle. So in a given clock cycle, it assumes that the data would be placed by the device, therefore it can simply take or store the data inside. So it works under the assumption that the device is faster and the timing is as per the master's clock. In the semi-synchronous one, a slower device can take more than one clock cycle in order to make the transfer happen. So the device may actually make the data available here, valid data that may be available here, but may also indicate through a signal that the data is available or it is complete, okay, like this one. Then the data can be stored in. In the asynchronous input, we don't have a common clock between the two devices. So first the device can put that it is ready. Then it is being acknowledged that it has been, the ready is being looked by the master. Then the corresponding data is being put. On seeing the data, the ready is being removed. Then the data is being strobed here. Then the acknowledgement is also being removed. So this interaction can happen. Then IO interrupts are extremely useful in order to make the save the processor times. So instead of the processor executing a wait loop, waiting for the status of a device to be updated, you can let the processor to execute any program that is currently it is doing, and when the device wants the attention, it can interrupt it. Okay. So when there is an interrupt that is being raised, then the processor must tell the device when to send the information, and then it gets into an mode where the request is being handled and acknowledged and the communication takes place. So here is an example of how a simple interrupt hardware can work. So there can be potentially two devices which can give rise to an interrupt. So it raises the interrupt by setting a flip-flop like this one. Then many interrupts from many devices can be ORed together, okay, and then an interrupt request can be given to the processor. So then when the interrupt is acknowledged, acknowledgement is being given, then the device which has been acknowledged places the interrupt vector, okay, which is being taken inside by the processor through the data bus, and the processor program jumps to this particular restart interrupt, and from there the interrupt service routine starts running. Again, daisy chaining method can be used to acknowledge the interrupt. That is, different devices can give rise to the interrupt like this one. They are being wired or, and a common request goes to the processor. When an acknowledgement comes to the processor, it is first handled by the device 1 which has the highest priority. If it has not given the interrupt, it will simply pass on this acknowledgement to the next device. But supposing it has given the interrupt, then it will consume this acknowledgement and it will take the bus and do the data transfer over the IO bus. Then the interrupt software can be as follows. Suppose you have got a character input device which reads character by character. First, the interrupt software or the ISR to do some initialization. Subroutine initializes the devices. Whenever a key is being pressed, an interrupt is being generated, then it enters an ISR. Generally what it does, it saves the state of the interrupted program, because when it returns back it can restore the state and handle from where it has left. Do the programmed IO operation by reading, writing, reading from the device and writing into the memory and so on. Then restart or turn the interrupting of a device and then return back by restoring the state. So far what we have seen is that IO transfer in which the memory is being involved. In the programmed IO, the memory keeps busy checking the status and then handles it. In an IO driven IO transfer, then also the CPU executes an ISR and handles the transfer. So from the memory through the IO device, it is always through the CPU. So the CPU acts as the link between or the mediator between the memory and IO, and therefore it is being occupied. We can look at a different scheme wherein the IO device can directly interact with the memory without disturbing the CPU, and for that you need another bus controller called as the DMA controller. So the DMA controller can take the bus and enables this operation to happen. So we have what is called as the direct memory access. It allows the external device to access the memory without the processor's intervention. So processor is being relieved. But for that we need a DMA interface device or a DMA controller. It must be set up and programmed, and the transfer is initiated. Usually the CPU sets up the DMA controller, telling what transfer has to take place. The steps the DMA controller might take to do a transfer of the block is as follows. It becomes the bus master. It asks the CPU to relinquish the bus by using a signal called hold, and on getting hold acknowledgement, it takes the bus, then sends the memory address and read or write control signal. So the data would be read from the or written from the memory and be available. Then it similarly issues the IO command of appropriate IO read or IO write. At the end of the transfer, it releases the bus. Okay, or probably after every transfer it may do it. After every transfer it does it, then it is called as the cycle stealing. While the processor is using the bus for accessing the memory, the DMA, whenever the bus is free, it steals the bus and uses it. Or it can do it by taking the bus for a certain duration and completing an entire block of transfer. Okay. During every transfer, it has to change the memory address. Typically, it increments the memory address for a block transfer after every memory transfer, so that it points to the next data item. It should also keep track of a count of how many transfers are over, so that once the block of transfer is over, the end of the transfer is being identified so that it can stop. A typical DMA controller will have the following structure. So it uses the address to identify whether address is actually meant for this controller. It decodes the address to identify whether this address is its own address. It can also use the read-write control signals. Then it can request the bus from the CPU using the bus request. The bus, if it is granted by the CPU, will be taken by this one. The bidirectional data bus is being used for data transfer between the CPU and the DMA controller. And again we have got another data bus for the purpose of transfer to device. So here an IO device is being connected. So it uses in its own registers the memory address, typically the starting address of the transfer, the count of how many bytes or words have to be transferred, then the control of whether it is read operation, read or write operations, and so on and so on. So here it issues the control signals to the DMA. Then a memory controller can be of two types. It may be a DMA selector or a DMA multiplexer. So here you have the processor, memory, and a bus. So a number of devices are being handled by a single DMA selector. So what it does, it selects one of the devices and makes the transfer, okay, by keeping track of the address and count of the block transfer. Or a number of devices can be handled by a DMA multiplexer by having a number of DMA channels, okay. So there will be a separate address and count register for each one of the devices, so it may multiplex the transfers on these buses. Again, the steps in DMA control will be very similar, okay. So processor initiates the DMA controller, gives the DMA device number, and then that is the DMA channel is being initialized. The DMA control starts the data transfer, obtains the bus through the arbitration, places the address and the appropriate control signals, completes the transfer, and then releases the bus. Every transfer it updates the memory address and the count and so on. Finally, through the status it intimates the processor when the transfer is over. A typical DMA controller along with an interrupt controller will have this structure. Here you have got the IO device, okay. If it is an interrupt, it gives rise to an interrupt request. The IO controller may get interrupt requests from many devices, and it may give a common interrupt to the CPU and gets an interrupt acknowledgement. Whereas the DMA controller uses the following signals: hold and hold acknowledgement to control to the CPU, data request and data acknowledgement between the IO device and the DMA, then IO read, IO write and commands for the IO, memory read and memory write commands for the memory. So the address bus is being generated, the address is put on the address bus by the DMA controller, but the data bus of the memory and the IO device are being directly connected. So based on the transfer, the memory can put the data and which is read by this IO device, or the IO device may put the data which is being stored into the memory. The normal way it works is that the data request is being generated. As a result, a hold is being given to the CPU, a hold acknowledgement comes, and then a data acknowledgement is being given, and a number of read write operation will take place. As it is illustrated in this timing diagram, first a data request is being given. In response to that, the DMA controller will give a hold request to the CPU. So the CPU may give a hold acknowledgement, then it gives the data acknowledgement to the device, then a address followed by a data transfer takes place by giving the memory write and IO read. For here it is the IO device from which the data is being read and goes to the memory. So you have got IO read and memory write. So this is one transfer, this is the second transfer, and so on. Finally, when all transfers have got over, end of transfer signal is being given. Then the external device, okay, can be of two types. It can be a parallel device or a serial device. A parallel device is one which can transfer more than one bit at a time. On the other hand, a serial device can only transfer one bit at a time. Again, the serial device can be, transfers can be synchronous or asynchronous. Okay. So the parallel devices are faster, but they may have the data skew problem. Okay, they have to be limited over small distance. Serial devices are cheaper and slower. So here is the serial to parallel or parallel to serial conversion that can take place. So here you have got the sender has got a parallel of 8 bits, but it has to be converted serially one by one bit at a time and then send here. Again the receiver collects all these bits, converts it, constructs a byte and then uses it. This is a serial transmission. In the case of parallel transmission, all these bits can be transferred in parallel by the receiver. So the bandwidth would be more, okay, in the case of parallel transmission. So again the serial transmission can be asynchronous or synchronous. If it is synchronous, then the sender and receiver must synchronize, okay. So it can be done using a phase lock loop. Block of data can be sent one by one. It can be more efficient and faster, but it is expensive. Asynchronous, each byte is coded, handshaking signals are required, start and stop bits are required, okay. There is no need for sender and receiver to be synchronized, okay. So this is an example of a synchronous transfer. Data is sent one by byte, one byte by byte or one word by word, okay, and a common clock is being used, okay, by the sender and receiver. Synchronization has to be maintained, whereas here it's an asynchronous transfer between the sender and receiver. Then we will see that external storage devices or secondary storage devices, for example the magnetic disks, the advantage is that long term storage is possible. It is a non-volatile storage, power is not required, and it is the lowest level of the hierarchy in the systems, low, slow, large and inexpensive. Generally it has got a rotating disk coated with magnetic surface, so there is a removable read-write head that moves and accesses the information, okay. Typically number 1 to 4 platters may be there per disk. Rotational speed can be varying depending upon the speed of the disk in terms of number of RPM, okay. The number of tracks per surface can also be varying, number of sectors per track can also be different, okay. There are certain characteristics of this magnetic disk which we have to keep it in mind. Then first is the seek time, the time it takes to position the head over the proper track, okay, which can be of 3 to 14 millisecond. Then the rotational latency, rotate the disk so that the desired sector comes under the head. Then the transfer time, time to transfer a block, okay, which can be of into units of 1K or 2K and so on. We may transfer a number of blocks using this one. And then the controller timing, the overhead involved in the disk controller is also to be accounted for. Now related to these secondary storage devices, two things that is of important is its reliability and availability. That is, reliability is dependent upon the mean time to failure, okay. From one failure, how long does it take on the average, or the mean time it takes for another failure to occur. So whenever there is a failure, the service is interrupted. So this mean time to failure, if it is large, then it is more reliable, okay. Mean time to repair is called as the MTTR. So during this time repair period, the service is not available. So availability is a measure of how much time on the average, what percent of the time the service is available. So it is given by this ratio, mean time to failure divided by mean time to failure plus mean time to repair, okay. So we are interested in increasing the availability as well as the reliability. So how do we do it, okay. One can use a better technology and go in for better devices. The other way is to use redundant array of inexpensive devices, okay. So that in short we use an acronym called RAID for it. So you use a number of inexpensive or less reliable disks and try to achieve or improve the reliability as well as the availability. So an array of small inexpensive devices is being used, okay, and the data is spread over multiple disks, and the advantage is that multiple access can be done and if there is an error it can be tolerated because reliability can be incorporated by having redundant bits. But availability can be improved by adding also more bits. Okay. So these are the two metrics we have already seen. So what are the different ways in which these RAIDs can be incorporated? The first is the level 0 RAID, okay, wherein there is no redundancy, but the parallel access can be made. Okay. So there is no redundancy or striping. So multiple smaller disks are being used as opposed to a one big disk. Spreading the blocks of the content you want to access is being stored in multiple disks. This is called as the striping. The advantage here is that multiple blocks that are required can be read in parallel. So 4 disks can be accessed in parallel. So in the same cost, what we have simply done is you are divided, instead of having one big disk, we have divided and had smaller 4 disks. So the speed of access, effective speed of access is being improved. There is no redundancy. If one of the disks fails, then those blocks cannot be accessed. So there is no redundancy in this one. So this is the nature, this is the feature of level 0 RAID. Then the redundancy can be incorporated by having a technique called as the mirroring, where you have got 4 blocks, okay, having many the contents. Then you have a set of blocks which mirror the contents of this primary disks. So those are called as the mirror disks, and their purpose is to just as a backup mechanism. So uses twice as many disks as RAID 0, that is 8 smaller disks in terms of 4 duplicate 4 1. So there is always 2 copies, okay, they are called redundant disks, okay. So cost is twice, but if one of them fail, you have a parallelly the other one which can be used. If one disk fails, the system can just go to the mirror and consume the data. Okay. Then you have got a scheme which is a combination of RAID level 0 and 1, wherein we use the concept of striping as well as the mirroring. That is, the blocks are being distributed over different smaller devices like block 1, block 2, block 3, block 4 and so on. So parallelly you can access it. At the same time you also mirror it by having redundant device disks. Okay. So combine the best of both methods. Data is striped across 4 disks and mirrored also in this one. So 4 times the throughput is achieved because of this striping. Okay. And redundant disks twice, cost is twice. Okay. But the writes have to be made to both the disks. Whenever you write here, you should also write into this one. So this is what will happen. If one disk fails, of course you have got the mirror for taking the data. So this is the nature of the RAID 0 plus 1 level. Then the RAID 3 level, wherein it is called as the bit interleaved parity schemes, where suppose you have got a byte to be stored, then you distribute that particular byte or a nibble, let us say 4 bits, you distribute it into 4 different blocks. The bit 0 will be present in here, bit 1, bit 2, bit 3. Then you use a additional block for storing the parity bit. Okay. The cost of the higher availability. Okay. So for n bits you have got one more bit, the additional cost is 1 by 1. Okay. And we call this, so with this protects this one. So this is called as the protection group. So for this protection group of 4, you have used one parity bit. You can also have one more protection group which can be overlapping also, and for each one of the protection group you have a parity one. Okay. So the write requires writing into the new data to the data disk as well as computing the parity and writing into this one. So this is the additional overhead that is being introduced. Okay. Can tolerate a limited amount of error, because in case there is an error, it can be identified by looking at the parity bit. So then what can happen is that, so if there is an error, by looking at the parity bit, the error can be identified. So that is the how it can tolerate. Then block interleaved parity is a one wherein instead of bit you use a disk for storing the parity disks as blocks. So you have got 4 blocks, okay, stored in 4 smaller devices. You use one more disk for storing the parity block for this 4 blocks. So 4 times this throughput is now possible by striping. The redundant disk is for every protection group there is one more there, okay. So but what you can do is while writing you can do some saving. Suppose you write into this block, by looking at what is being written and by calculating the parity we can find out whether the parity bit has to be updated or not. So only if it is to be updated we will update it. So that can be done, but still it will be a bottleneck. Again, can tolerate a limited amount of disk failure. Then distributed block interleaved parity. So here the parity block itself can be interleaved. So that is the different in this one, instead of storing it in one place, okay. For example, here you will see that if the same disk is being used for storing parity, every time you write into any disk you have to change the parity block, access the parity block also, but the parity blocks are being distributed in this case, okay. For example, 6 and 9 are being used, okay. We will see this one. So there is a difference between the RAID 4 and RAID 5. So here you parity blocks, see this parity block is being distributed, you have here as well as here, whereas here this is the parity blocks, all P0, P1, P2, P3 are all present here. So whenever you write into either this or this, you have to access this device, whereas here when you write into 6, correspondingly P1 is being referred, when you write into 9, P2 is being written. So this is no more a bottleneck. So that is the advantage of this one. So I will stop at this point. So we have looked at the IO subsystems as well as the virtual memory design. So I will stop my lecture at this point. Thank you.